Hey guys, welcome back. This is Coach Miller.
And Mr. Bunting.
And we're going to talk to you a little bit about percent yield and theoretical yield and do a little more math for Unit 9. So let's jump right into this. What is percent yield, Mr. Bunting? Why is that important?
Well, the percent yield is going to tell us how efficient and effective we were inside the lab. It tells us how much product we get based on how much chemicals we use. So it tells us if we're using too many chemicals or if we're using just the right amount.
So basically we want to try and use the least amount of material at the beginning to get as much of my product that I want to try and get at the end, right?
Exactly.
Awesome. So there's a mathematical way that we can figure that out, right? And it's right here. So this is the formula that you need to know. Percent yield is actual over theoretical. What is that all about?
Well, the theoretical is done with a stoichiometry we did in the last video. So you got to actually go through and do your dimensional analysis and your mole ratios to find the theoretical yield.
So is that like a perfect world?
That is the perfect world. That will give you, if you get the theoretical yield, you have 100% efficiency. That's your ideal situation.
Cool. So our actual yield is what we do in the lab, and our theoretical yield is perfect world settings, or 100%.
Right. And if we give you a word problem, there's more than likely the actual yield will be given to you inside the problem.
Okay.
So that's what your given will be.
Cool. So I think we have a problem here. Can we just jump right into that?
Let's just jump right into it.
All right. So we've got the reaction of a combustion reaction. Octane reacts with oxygen to give us water and carbon dioxide. We are told that it's only 74.3% efficient. So that's not too bad, but it's not great. So if we actually expect to form, how many grams of water would you actually expect to form if 90 grams of octane are burned? So what's the first step here? What do we have to figure out?
I think the first step is recognizing that this is a percent yield equation because it gives us our percent efficiency right up here, the 74.3%. So based off of that, I can go right into my equation. Percent yield equals actual yield over theoretical yield.
Okay. So now we have to figure out our perfect world, our theoretical yield, right?
Our perfect world scenario.
Okay.
Okay.
So we start with what we're given in the problem, right?
What were we given?
We're given 90 grams of octane.
Which one of those is octane? The C8H18 or the O2?
Well, I'm pretty sure that this is oxygen, so I'm going to go with this.
Okay.
So if we start with 90 grams of C8H18, then we want to figure out how much water we actually produce, right?
Right.
So
that's what the question asks.
We've got to use our mole bridge, right?
Right.
Okay, so go from grams of octane to moles of octane, right?
Right. So far, so good.
And then we can go from moles of octane to moles of water in my mole bridge. And finally, we want to find out how many grams, right?
Right.
Okay, so we can go from moles of water to grams of water. Now, I haven't put any numbers in there yet, but we can go back and fill those in. 1 mole of octane, that's a lot of atoms there. What would be the mass of octane?
You take 8 carbons and 18 hydrogens, that'll give you 114.26.
114.26, okay. And for this section, we want to use our mole ratio, and we get that from our balanced equation up here, right?
Mm-hmm.
So
correct.
2 moles of octane will give me 18 moles of water.
That's a lot of water.
That's a lot of water. How many grams are in 1 mole of water?
I've done this so much I know it right off the top of my head.
Okay.
18.02. Don't even have to look it up.
18.02. I guess I'll take your word for it. And so we're good, right? We've got grams of water from 90 grams of octane. We just need to do the math here.
Yeah, let's just make sure everything cancels. We have grams of octane and grams of octane. Moles of octane and moles of octane. Moles of water and moles of water. We end up in grams of water, which is actually what the question asked for, grams of water. So yeah, I think we're good.
Awesome. So if we plug this into our handy-dandy calculator, we get what for our answer?
We get 127.7 grams of H2O. Remember, we multiplied all the top numbers and divided it by the product of all the bottom numbers.
Okay, so this is our theoretical yield.
Correct.
And we know our percent yield, right?
Uh-huh.
So we can plug those values into our formula, and it'll look a little something like this. Wrong side there. Let's put our actual, let me just move that down so we have room. So our actual yield is what we're looking for. Our theoretical yield was 127.7. Awesome. So using algebra, I know that if I'm trying to get rid of a fraction, I can just multiply, right?
That's how I would do it, but do we need to change that 74.3 first, or can we just multiply 74.3 right off the bat?
Well, yeah, we would need to change it because it is a percentage, right?
So how do we make that into a decimal?
Well, I know that a percentage is out of 100, so I can divide it by 100, right?
Right.
Okay. So I would move the decimal 2 places.
Okay. So
So
0.743.
0.743 times 127.7 would give me my actual yield, which is what?
94.9 grams.
94.9 grams. So, have we figured out how many grams of water we would actually expect to make?
Yep, we would have gotten 94.9 grams of water if we reacted 90 grams of liquid octane.
Awesome. So, there's our percent yield problem. And we can jump right into something else, right?
Yay. Moving on.
So, limiting reactants. What in the world are limiting reactants?
Well, limiting reactants are the reactants that are going to limit the amount of product you have. In other words, they are the reactants that are going to run out first in a chemical reaction.
Okay, so it's kind of like if I was in the kitchen making something like cookies or a cake or whatever. If I run out of sugar or if I run out of something like that, that'll affect how many cookies I can make, right?
That's exactly right.
Awesome.
Cookies are delicious, by the way.
Yes, cake is. Cake is better, I guess. So, how do I know? I mean, the question here, how do I know if I have a limiting reactant problem?
Well, limiting reactant problems are easy to see because you have to have the amounts of both reactants in your chemical equation.
Okay. So I know what I start with, but I'm trying to figure out how much I would end with.
Mm-hmm.
Okay.
This sounds like more stoichiometry to me.
So let's jump right into the steps there, because I'm pretty sure there's going to be a lot of math on the next slide.
Oh dear.
So steps to solve limiting reactant problems, we have to find the theoretical yield.
That means stoichiometry.
Okay, so theoretical yield is our perfect world yield, right?
Perfect world scenario. Do we have to take two theoretical yields since we're given two reactants and the amounts of both?
That's true. We would have to do two theoretical yield problems to figure out which one would give us the least amount of our product, right?
Right.
Okay.
So once we've done that, how do we figure out which is the limiting reactant?
Well, I guess it would be the one that produced the least amount, right?
Right, that seems logical.
Okay. So the one producing the least amount is our limiting reactant, and then we can figure out how much of our limiting reactant is left over.
That seems pretty easy. If the limiting reactant is the one that limits your reactant, it's not going to have anything left over because you ran out of it.
Okay, so it all gets used up. But does the other reactant all get used up?
No, we have excess of that reactant left over.
Okay, so we'll have to figure that out.
Okay. We'll show you how to do that.
All right, so here's our problem. 15 grams of hydrogen are mixed with 40 grams of oxygen and we form water. So first problem is we've got to write our balanced chemical equation, or a reaction.
Man, that Unit 7 stuff. Alrighty, how do we do that?
Well, I know hydrogen and oxygen are mixing together.
Are those special? Is it just going to be H plus O? Or are those diatomics?
Yeah, those are our special elements that form that 7 on the periodic table. So I know hydrogen is H2, and oxygen is O2, and I know they're going to produce water, and water is always the same. It's H2O.
Okay.
Or we could call it dihydrogen monoxide.
We could call it that.
It sounds a little more interesting that way.
I hear it's dangerous.
So now I want to balance the equation. I want to have 2 oxygens on each side, and then that would give me 4 hydrogens on both sides. And we're good, right?
Right.
So we've got to first calculate the theoretical yield.
Okay. Let's go ahead and start with hydrogen, since it's the first amount of reactants given. So we're going to take mass of our hydrogen to find the mass of our water.
Okay, so I'll have to go from grams of hydrogen to moles of hydrogen.
Uh-huh.
So 1 mole of hydrogen is 2 atoms, and that'd be 2.02. And then we can go from moles of hydrogen to
Moles of
moles
water.
of water.
Our mole ratio, mole bridge.
And that's 2 to 2, or 1 to 1 relationship. We'll go ahead and write it 2 to 2. And lastly, we want to get grams of water, right?
Right. There's 18.02 grams of water, or moles, 18.2 grams in every 1 mole of water.
Okay.
I see that a lot. Let's put that into the calculator, and we get 133.8 grams of water.
That's a lot of water.
That's a lot of water, especially just from 15 old grams of H2.
15 grams of hydrogen gives us 138 grams of, or 133 grams of water.
That's crazy. Let's find out what oxygen does. We started with a lot more, 40 grams of oxygen.
So maybe we will end up with more water.
Well, that makes sense. We start with more, we end with more. But let's see what the math actually does for us. So we got to go to moles of O2, and each oxygen weighs 16, so we have 2 oxygens, so it's 32 grams every 1 mole of O2. Convert between oxygen and water with our mole ratio, and now we have 1 mole of oxygen for every 2 moles of water. Be careful where you put those numbers.
Okay, so this might actually affect how much water we have,
Oh no.
because now this number is a little different.
Uh-huh. We'll see what happens. And then the end part is always the same, 18.02 grams of H2O every 1 mole of H2O. And we plug that into our calculator, and this time we only get 45.05.
45.05 grams of water. Yeah, so, wow, we start with more oxygen, but we actually produce less water.
So this means I can't figure this out without doing the actual math.
Cool.
So the next part of this question was finding out which was the actual limiting reactant, and how do we know? Well, we take our smallest product, so 45.05 is obviously less than 133.8. So what reactant made 45.05 grams of H2O?
Oxygen.
Oxygen. So oxygen has to be your limiting reactant, because that is the most you can make. Because you will run out of oxygen before you can make any more.
Okay.
Okay? So how many grams of our limiting reactant are going to be left over? Well, if it's limiting the reactant, it means it runs out. So we have 0. That answer is always 0.
So we're always going to use all of our limiting reactants.
Always and forever.
Okay.
Okay. But how many grams of the excess reactant are left over? How do we do that?
That's a good question. Well, we got to know how much we start with. We got to know, maybe we're going to do a little bit more stoichiometry.
Ooh, yay. Can't wait. But what do we start with now? We've already used both of our reactants and found out how much water we can make, so how do we go back? What is our excess reactant?
Well, our excess reactant, we would have hydrogen left over.
So if oxygen is the limiting, the other one has to be the excess.
Yeah.
So
So oxygen is going to determine how much hydrogen I use.
Okay.
So do I need to start with oxygen?
Let's start with our amount of product, the maximum amount of product we can make, which is 45.05
Okay.
grams of H2O. And then let's just see how much hydrogen we will have left over, or how much hydrogen we'll actually use.
Oh, so we're actually going to kind of go backwards.
Going backwards this time.
Okay. So we're going from grams of H2O to grams of hydrogen.
Yes.
I see. So we'll use the mole ratio and go backwards
Okay.
across that bridge.
I'm getting really good at this stoichiometry stuff, Coach Miller.
The more practice, the better we get, right?
The better we get, the less tutoring we have to attend.
Moles of H2.
H2.
So moles of water is 2, moles of hydrogen is 2, and then I can go to grams. I know 1 mole of hydrogen has 2.02 grams.
Okay, plug into a calculator, and we get 5.05
5.05 grams.
grams of H2. Now, what does that tell us? 5.05, is that how much we used, or is that how much we have left over?
Well, I'm assuming because we used up all of the oxygen and we produced that 45 grams of water, that would be how much we have left over. Right?
I thought it was how much we used.
Is it?
I think so.
Yeah, that's right. So
So we have
I
to
would
use.
I would use 5.05. Okay, I got you.
So, but how do we tell how much is left over if we used 5.05?
Well, I know in my problem I started with 15 grams, and if I used 5.05, then I can just subtract the 2, right?
Right. Let's do that. See what we get. So 15 minus 5.05 gives us 9.95 grams.
So we actually have 9.95 grams of hydrogen left over.
All right.
All right, so if this reaction is done in a laboratory environment and we produce 43 grams of water, what was the percent yield? So now we're going to go back to our percent yield equation. I know that's actual over theoretical. And if I plug all of these values into my calculator, I know I actually produce 43 grams. But theoretically, my perfect world, I create 45.05. And I can divide those, and that will give me 95.4%. So actually a pretty efficient reaction there. Actually a pretty efficient reaction, so 95.4% efficient. So there you have it, percent yield, theoretical yield, and percent composition. So hopefully this will help you guys as you are looking at some more practice problems, and we'll see you again next class.